Alright, so motion, more than straight line motion. Straight line motion, whether it was horizontal or vertical or on an incline, if it all occurred on a straight line, we were perfectly fine using simply plus or minus to represent the vector. Positive x direction versus negative x direction, and so forth. But in general, a lot of motion isn't on a straight line. For example, if we hit a baseball, or even throw a baseball, the baseball follows a trajectory. It's parabolic. So the position of the baseball, if we put our origin at the location where the baseball was hit or thrown, whichever we happen to do to it, the position of the baseball at any point in time is changing. But the position will have an x component and a y component. Sometime later the ball's over here. So its position is that way. It has an x component and a y component. So when we talk about motion in 2 dimensions, which is similar to motion in 3 dimensions, really, we need to deal with the vectors in terms of their components, so their x and y components. We're not really going to do much with 3 dimensions at this point in time, though the equations we derive would work for the 3rd dimension as well. But 2 dimensions is enough, I think, at this point in time. So when we talk about position, the position vector, I'm not going to call it x by itself, or I'm not going to call it y. The reason why is x generally means an x component. Generally means horizontal. So our position vector can be written as an x component, I hat, plus y, which is the y component, j hat. So our position vector can have both x and y components, technically z component as well. Velocity. To represent the x component of our ball's velocity, we'll use a v with the subscript of x on it. To represent the y component of the velocity, we'll use a v with the subscript of y on it. So v still means velocity, but the subscript is going to tell us which component. So this ball, when it is hit, its velocity is tangent to the trajectory. So its velocity has an x and a y component. As the ball continues through its motion, its velocity is always tangent to the trajectory. So the velocity has x and y components as well. Acceleration, similar to velocity, we'll use an a with the subscript of x to represent the x component of the acceleration. We'll use an a with the subscript of y to represent the y component of the acceleration. Now we're still going to ignore drag for now. Case of a baseball, that's not as good of an assumption. Drag does definitely play a role. But again, it's complicated to work with. So we'll look at an ideal situation right now. For the example of the baseball, if there's no drag, there's nothing to slow it down or speed it up horizontally once it has left the bat. The x component of the acceleration in that example would be 0. We'd have, if there was drag, which realistically there is, then the x component of acceleration would be negative, because it would serve to slow the ball down horizontally. What about the y direction? Acceleration of gravity, negative 9.8 meters per second squared, exactly right. Okay. The calculus relationships that we talked about are still perfectly valid. Velocity is still the derivative of the position with respect to time. That's absolutely true. Looking at our position function, the velocity will be the derivative of this first term. X is a variable, x is changing. I hat is not changing. It always has a length of 1, and it always points in the x direction. So that's a constant. So we get dx dt I hat, plus, in the second term we end up with dy dt j hat. Okay with that? What this means, we already said that the velocity vector would be some x component I hat plus some y component j hat. What that means is the x component of the velocity is dx dt. If you take the derivative of the function that describes just the horizontal motion alone, you will get a function that describes the velocity in just the x direction. This part, dy dt, is the y component of the velocity. Which is interesting. What this means is that the velocity, the horizontal velocity, the x component of the velocity, has nothing to do with y. The vertical motion is irrelevant as far as vx is concerned. And vice versa, vy is independent of x. Okay? Next step, acceleration is still the derivative of the velocity with respect to time as well. Taking the derivative of this or that, it doesn't really matter. If we take the derivative of this, we're going to get the second derivative of x with respect to time. If we take the derivative of this function, this vector will have the derivative of the x velocity with respect to time. Similar to what we end up with velocity, this first I hat term, this x component, is the x component of the acceleration. This is the y component of the acceleration. So the calculus relationships are still perfectly valid, but they're valid along one axis at a time. They're valid along the x-axis, they're valid along the y-axis, but we can't interchange the two. Okay? All right. If the calculus relationships are the same, then if we have a situation where acceleration is constant, and we work backwards and integrate, we will end up with the same set of kinematic equations we ended up with before. Okay? When we integrate our velocity, acceleration to get velocity, we'll have this function. The velocity at any point in time will equal the initial velocity vector plus the acceleration vector times time. So that kinematic equation is still perfectly valid as a vector. So that means we need to write the velocities in terms of their x and y components. We need to write the acceleration in terms of its x and y components as well. If we do that, so we have a final x component of velocity in the x direction. We have a final y component of velocity in the y direction. Initially, we'll say Vx naught to represent the initial velocity in the x direction. Vy naught will be the initial velocity in the y direction. Acceleration, x component, y component. Time is a scalar. It's just a number. It's like multiplying your vector by 2 or 3. So the scalar just factors in and multiplies by each component individually. So what we end up with when we add these vectors on the right-hand side of the equation, just like we've done with other vector examples, you only add the x components together, and you only add the y components together. So, for example, here, the x component of the first vector is vx naught. The x component of the second vector will be ax times t. So that's summing the two x components. That will be the resultant x component. Y components, similarly. Now this actually works out quite nicely. This x component on the right side, what does it equal on the left side? What's on the left side? X components determine which component? X components. The x component on the left side of the equation has to equal the x component on the right side of the equation. What that means, Vx is the x component on the left side of the equation. Vx naught plus axt is the x component on the right side of the equation. That means the final position, the final horizontal velocity depends only on the initial horizontal velocity, the acceleration horizontally, and the time. Exact same kinematic equation we had before, but only valid for the horizontal aspects, pieces of motion. If we set the y components equal to each other, we get a similar equation. The final velocity in the y direction depends only on the initial velocity in the y direction, the acceleration in the y direction, and the time. The horizontal motion is independent of the vertical motion. There's only one thing they share. What do they have in common? Time. Exactly right. However long it's in the air vertically is how long it's in the air horizontally. That's the only thing they share. Okay. If we integrate our velocity function, we'll get a position function. That looks just like the kinematic equation we've already used. Using r in this case to represent that it has both an x and a y component. If we follow the same steps, plug all the vectors in terms of x components and y components, the x components on the left side have to equal the x components on the right side. The result is that for the x components. If I set the x components equal to each other, the final horizontal position depends upon the initial horizontal position, the initial horizontal velocity, the horizontal acceleration, and the time. I get a similar equation for the y, for vertical motion. So basically we're ending up with the exact same kinematic equations we've already used. The kinematic equations from chapter 2 are perfectly applicable if you use them for the horizontal motion alone or the vertical motion alone. Okay? And of course, the same rules apply. Acceleration has to be constant. If acceleration is not constant, you have to go back to the calculus relationships. The third kinematic equation we have, the v squared is equal to v naught squared plus 2a change in x, still applicable. For x alone, for y alone. Okay, questions so far? We might start falling together as we do some examples. Make a little more sense. I want to show you a demonstration first though. this little contraption, I'm going to put, I have two little steel balls. They're identical, same radius, same mass, everything about them is the same. I'm going to rest both of them on, one on this hole and one on this hole. When I press the button, this thing flips. So what happens is that the ball that's sitting on this hole, the bottom, it's like pulling the tablecloth out from underneath something. If you do it really fast, the object sitting on the table will stay in place. The ball that was sitting on here is going to stay in that location. Now it has no support, so it's going to fall. So basically, this ball will fall, just fall at rest. Starting at rest, will fall straight down to the ground. This ball over here gets hit by the lip. So as this metal bar rotates, it's going to hit the ball, thus it's going to push the ball horizontally outwards. It doesn't push it up or down, just horizontally outwards is all. Okay? So I want you to think what's going to happen. Now this one's kind of hard to see. It happens pretty darn fast. So it's more a matter of listening to what happens. Let's see if I can hit the gap over here. Thank you. What'd you notice? They hit the ground at the same time. We heard the clicks at the same time. But one had an initial velocity and the other one didn't. Right. One had an initial horizontal velocity, but both had an initial vertical velocity of 0. If they have the same initial vertical velocity, they have the same initial position, they're both under the influence of gravity, they're both going to end up at the same place, the time has to be the same for them. So they hit the ground at exactly the same time because all their vertical information is the same. It didn't matter that one was pushed outwards and had a horizontal velocity. The one that had a horizontal velocity ended at some distance from the table. So it ended up hitting the ground further away from the table than the other one did. What about their final velocities? Total, overall final velocity. Were they the same? No. Take a guess.
Yeah. No.
What determines velocity? Speed and direction. So number one, they weren't headed the same direction. One fell straight down, so its final velocity was straight down. One shot outwards. It had a component of velocity straight down, and it had a component of velocity horizontal. So its final velocity, the one that was shot horizontally, it had a final x component and a final y component. So its magnitude, using the Pythagorean theorem, is going to be bigger than the one that just had the y component. That make sense? So the one that was shot horizontally will certainly be traveling faster, but it hits the ground at the same time because the y information is the same.
That's only true on a small scale, though, right? I mean, if you shot a bullet and you dropped the bullet, obviously the bullet.
If there's no drag, the same thing would happen.
I guess I can see what you're saying. No drag.
Yeah,
Okay.
that drag is the
You're right.
hard to get rid of. We really don't have a way to get rid of that unless we travel to the moon, which would be fun. But it's less gravity, but with no air resistance, we could do the example with the bullet.
Did they actually do that with a feather and a hammer on the moon?
Yes, they did, and I have the video clip. I need to remember to bring it in. They actually took a feather and a hammer, astronauts standing on the moon, and they decided to test this. Well, the moon has basically no atmosphere, so it has no drag. So when they drop the hammer and the feather, they hit the ground at exactly the same time.